So before I get into the third example, I just want to review some pre-algebra stuff that we'll have to use, and I'm trying to explain it here so that when we get through into the example, um, I won't have to do some over explanation and accidentally make you guys feel overwhelmed with it. So in pre-algebra, you guys learned a um, rule for exponents where if you have um, x to the a what was it times x to the b. If you have the same base, the rule was that you can add the exponents together, and so we can do this. So in the example I'm eventually going to work on, we're going to have to go in this direction. We'll have something that looks like this. We have a variable or value to some two exponents, and we're going to have to break it down into two terms. So I'll tell you guys ahead of time that in our example, we're going to have something that looks like this. And what we'll want to do is to break this apart using um, this rule with exponents. So what it will become here is using the right side. The right side said that I can break this into x to the a times x to the b. So for this one, it'll look like this: e to the x to the fifth over 5 um, times e to the c. And what I want you guys to take a look at here is that we actually have a constant. This e to the c is just some value. E is an actual number. It's 2 point something. What was it? E, the value of E is approximately 2.71828. So this is a constant to a constant. So we want to think of this together as just one constant. So we'll just combine this. I'm going to replace this with a big C. So what happens is now this expression becomes C times e to the x to the fifth over 5. So we'll have to do this within our example, and we're going to be using this to eventually solve the differential equation. So I'll go back to that when we work through the example. So going back to example number 3, our differential equation here is x to the fourth y minus 2, and we want to find the particular solution given that the initial condition is 0, y of 0, 0, which is, we can think of just a point as 0, comma 0. So we're going to use the method of separation of variables. So the first step is to separate. So just like the other one, I'm going to just be consistent. I'm going to multiply both sides by dx. And that means that these two dx's will cancel out. And then what I have left is dy equals x to the fourth y minus 2 dx. So now I want to bring this factor of y minus 2 to the other side. Since it's being multiplied to the x to the fourth and to this dx, the only way for me to bring it over is to divide it over. So I'm going to divide both sides by y minus 2. Okay, then it will cancel out from here and here. So I'm going to rewrite what I have. So technically here on the left side, this y minus 2 is in the denominator of dy. And so I'm going to write it like this. I'm going to write it like this: y over y minus 2 dy. I want to write the dy so it's being multiplied to this instead of keeping in the numerator. And then the right side will be x to the fourth dx. So that's the separation step. I know I did the separation correctly because on the right side I just have terms with x in it, and then on the left side I have terms with just y. So the second step is to integrate. Okay, so I'm going to rewrite this. 1 over y minus 2 dy equals x to the fourth dx. So each time I'm going to integrate it, and each itself is a integration problem. So at the integrations problem, you can use the power rule for the antiderivative, and you may need to use substitution is what we're actually going to have to use to integrate the left side here. So I'm going to do that first. So I'm going to make a side problem. I'm going to write the first integral on the side and just work through u substitution, and this will be a good opportunity for you guys to review it. So here I'm going to let u equal to y minus 2. Therefore, du equals 1 dy, and the derivative of negative 2 is 0. Therefore, dy equals 1 du. Now I'm going to rewrite the integral. So I have integral of 1 over my u, because I'm plugging u for the y minus 2, and our dy we found in this step here is just du. So the integral of 1 over u is ln the absolute value of u plus c. And then I'm going to plug back in my u, so it'll be ln the absolute value of y minus 2 plus c. So this is the answer to this integral problem here. So I'm going to bring it back over and write underneath. So we'll have ln, the absolute value y minus 2 plus c equal to, and now I need to integrate the right side, and I can use the power rule for the antiderivative, so that will become x to the fifth and the coefficient is 1/5, and I'll have plus c. So this is again, like I said before, these two are different constants, and I'm just going to now solve. I'm going to bring these two constants together. So I'm just going to subtract c1, and this will happen every time. So this will be 0, and then these two, I'm just going to put them together as one large c. So my equation, just cleaned up a little bit, will be ln y minus 2 plus, equals 1/5 x to the fifth plus c. Okay, so for the third step in the previous example, I had solved for c first, but in this case, it's going to be easier for me to solve for y and then solve for c. So I'm going to switch the last step and solve for y first. So the equation we have so far is ln of y minus 2 1/5 x to the fifth plus c. And the way I want to get to this y here is right now the y is, I'm taking the ln, so I'm going to have to undo the ln first, and then I'm going to have to work with the plus 2. So the way I'm going to do this is, in order for us to undo the ln on both sides, we'll have to do what's called exponentiate both sides. So I'm going to, all these are going to become the power of e. So these are the exponents of e here. And I guess just to make it clear, I'll put parentheses around it, but these are the exponents of e. So the idea is, from algebra 2, you guys learned that e and the natural log, they cancel each other out. So from here, the e and the ln will cancel each other out. And so what we're left with here is going to be the y minus 2, the absolute value signs drop, so you have y minus 2 equal to e to the power of 1/5 x to the fifth plus c. Alright, so this should look familiar. This is something that I wrote up in the beginning of the video right here. So we found that if we rewrite this, we'll get it to be c e to the x to the fifth over 5. So there's a little kind of algebraic complexity here, so you guys should take a minute and make sure you understand it, um, and and just pause the video and just understand this process, because I'm not gonna go through it again. I'll just make the video longer. So I'm just gonna take the result from our work there, and I'm gonna replace it here. So we have y minus 2 equal to c e to the 1/5 x to the 5th. Okay, so now remember our goal is to solve for y, so now I can add the 2 on both sides. And so what we have is y equal to c e to the 1/5 x to the 5th plus 2. So we sort of did like the ending step where we solved, in the previous example, we had solved for y as the 4th step, but here we're solving for y as the 3rd step. And then we're going to solve for c here because it's going to be algebraically a little more easier. So for the 4th step, we're going to solve for c, which originally was solve for y, but now we're going to solve for c using the initial condition of 0, 0. So we'll have 0 equal to c e to the 1/5 times 0 to the 5th plus 2. This is still going to be 0. E 1/5 to the 0 to the 5th, that's going to become 0. And then e to the 0 is 1. So what we have here is c plus 2. And that implies that c should equal to -2. Okay, so now we're going to present our solution by plugging in our particular solution into the general solution. So this is the general solution. And then we're going to plug in this initial condition in for c here into the general solution to get the particular solution. Therefore, our answer is y equals -2 e to the 1/5 x to the 5th plus 2. So just to visualize this solution, just going back to the slope field here, the equation that we just got is the solution. There's a graph of this function here that passes through 0, 0, which was our initial condition.